Alright, we're going to actually go into horizontal asymptote. He's the partner in crime for the vertical asymptotes. And in calculus, when we talk about a horizontal asymptote, we're talking about limits at infinity. And so just to remember, a horizontal asymptote is the ones, oops, wrong one. Horizontal asymptote is where as I go to the ends of my function, I'm approaching some sort of y value, usually we kind of use a dotted line that's a horizontal line. And so just to kind of give you an idea, we're talking about something that looks like this. And so a function that kind of comes up and then comes down, and what I'm looking at is way over here in negative infinity area and then way over here in positive infinity area. And I want to see is my function approaching some sort of y value. And in calculus, we're using this to describe horizontal asymptotes as limits at infinity. So we're as x is at infinity, that's what we're looking at. And the way that we prove a horizontal asymptote at y is equal to c, we say that the limit of f of x at x approaches positive infinity is equal to c. And the limit as x approaches negative infinity of f of x is equal to c. So we're looking at what is it like way over here in the negative infinity area, is it approaching a number, or way over here in the positive infinity area. And you have to think about, this is talked about end behavior, and so we're looking at end behavior that will approach some sort of y coordinate. And so when we talk about limits at infinity, I gave you a graph. We're talking about, does it level off? Does it approach some sort of y value? One end, both ends, or none at all? Analytically, we usually just substitute in, or if it's a rational function, I gave you a shortcut in number 3. So essentially what I mean by rational function is I have y is equal to some sort of f of x, a polynomial divided by another polynomial. That's what I mean by rational function. And so if it's top heavy, what we're talking about is the limit, the growth rate on top is so large that the limit's not going to exist. It's just shooting off to positive infinity or shooting off to negative infinity. If it is bottom heavy, then that means my growth rate is really large on the bottom, so that means my limit is going to 0. My top is so much smaller that my bottom's so large that my fraction is approaching 0. If my polynomials have the same degree, that means my growth rates are the same. And so we're just going to looking at the leading coefficients, and that's going to create a ratio or a fraction. That's what we're going to look at. You have to be really careful because functions a lot of times behave really strangely, especially with rational functions. I have a couple examples that I'll show you. You have to also be really careful with negative infinity, especially when we square it or raise it to the fourth, because negatives that are squared become positive, so just be really careful about that. Finally, we have what happens if we have functions that are logarithmic, polynomial, and exponential. So let's talk about their growth rates. Let me give you a quick little graph. A log function actually grows pretty slowly. He gets pretty flat as he goes to positive infinity. If I have a polynomial, let's say for an example a quadratic, he shoots off to positive infinity on both sides. So he grows pretty quickly. He grows a lot faster than my logarithmic. Finally, my exponential, he's my quickest growing. He shoots up to infinity pretty quickly. And so when you look at these three, just be careful on if you're comparing which one's which. If you have a quadratic over a logarithmic, well, my quadratic is going to grow so much faster than my log, and an exponential is going to grow so much faster than a quadratic or any other polynomial. So for the following, we're going to find the horizontal asymptotes and evaluate the given limit. So let's look at number 1. If you notice, number 1 has 2 quadratics. I have a quadratic over a quadratic. And notice that the degrees are the same. Well, if I was going to simplify this, I would write the limit as n is going to infinity of 4n squared divided by n squared. My growth rate for a quadratic is so much higher than the growth rate of a linear function. Notice that I have a linear function located over here, and I'm not really concerned about that guy. He doesn't grow as fast as an n squared. If you notice with our function, we have n squared over n squared, and I gave you a little trick where if my growth rates are the same, meaning my degrees of my polynomials are the same, I just go ahead and cancel. And what that shows me is my limit as my function gets really, really, really large out to positive infinity, the y value that I seem to be approaching is equal to 4. And so when we talk about a horizontal asymptote, we're talking about where y is equal to 4. So as my function gets really, really, really large, way to the right, it's going to approach the value of y is equal to 4. Now let's go over and look at number 2. Notice again, I'm going to go ahead and box the highest degrees because we want to compare their growth rates. And so I have a 2x over a 3x squared. So I have a linear function over a quadratic. And so I'm just going to go ahead and just kind of focus in on those. With my linear function, I have a 2x. With my quadratic is 3x squared. Well, again, if I showed you that if it's bigger on the bottom, the growth rate is so much bigger on the bottom that my function is going to be going to 0. And so if you want to think about it, I have a really small number, say 1, over a really large number, say 10 million. And so what is 1 in comparison to 10 million? Well, not very much. That's where the 0 comes from. So 1 over 10 million is pretty darn close to 0. So that's where that idea of this limit where it's bigger on the bottom is going to be equal to 0. Alright, I went ahead and erase. Oops, I forgot to write. So we had that, that growth rate we already talked about. And we said that's going to be equal to 0. I forgot to go ahead and tell you guys. So my horizontal asymptote is going to be y is equal to 0. Sorry about that. Alright, number 3. So let's go ahead and compare. And so I have a growth rate of 2x to the 5th over negative 5x squared. Well, notice that my growth rate on top is so much bigger than my growth rate on the bottom. I know 2 is bigger than negative 5, but that x to the 5th, he grows pretty quickly. He grows significantly more than that x squared. And because of that, since that growth rate is so large on top, my function is essentially going to either positive infinity or negative infinity. Well, if I plug in infinity to the 5th is just infinity. And so we're saying this is infinity, or you can write dne. So my horizontal asymptote doesn't exist. Number 4. Number 4 is one of those ones that behaves pretty strangely. And so let's go ahead and look at it. I have a growth rate of x and then another strangely growth rate. I don't really care about that 1. What I do care about is the square root of x squared. And if I was just kind of focusing on those two, I wanted to simplify, I would probably write the limit as x approaches infinity of x divided by the square root of x squared. Well, if I plug in infinity squared, this is going to give me a positive number in here. So if I plug in that infinity, I'm still going to get a positive. Not that it really matters because infinity is positive in this case. It won't be so in the next problem. But if I was going to simplify this guy, the square root of x squared is just going to be, x. And so x divided by x is equal to 1. And so my horizontal asymptote in this case is y is equal to 1. Number 5. Notice number 5 is very similar to the one we just did. However, instead I have a negative infinity. So let's go ahead and look at those growth rates. And so I have an x growth rate and an square root of x squared growth rate. Well, if I was going to simplify this guy, what I'm looking at is the limit as x is approaching negative infinity of x divided by the square root of x squared. Well, if I was going to plug these guys in or simplify a little bit further, I essentially have the limit as x is approaching negative infinity of x over, well, if I was going to square in negative infinity, that gives me a positive infinity, and the square root of positive infinity is still infinity. So essentially I'm getting essentially the absolute value of x. But when I plug these guys in, I get a negative infinity over a positive infinity. Well, that's equal to -1. So my horizontal asymptote is going to be located at y is equal to -1. So now let's go over to number 6. In number 6 I have an exponential, and if you remember I drew an exponential for you, and so an e to the x looks something like this. And e to the x, if you look at it, as he approaches negative infinity on this side, he's getting really close to 0. And so if I plug in, I'm going to go ahead and do direct substitution. So if I plug in negative infinity, so I have the limit, actually I'll just go ahead and erase that. I'm just going to directly plug in. So if I plug in negative infinity, I have as e is going to negative infinity, I'm pretty much approaching 0. And I'm subtracting, let's go ahead and plug in negative infinity squared plus 5. Not that 5 really matters that much in comparison to infinity. So I have 0 minus negative infinity squared. It's just going to be positive infinity, but I'm still subtracting. I don't really care much about 5 because he doesn't really matter that much. And so I have 0 minus infinity, which is equal to negative infinity. So in this case, my horizontal asymptote doesn't even exist. Number 7, if the graph of y is equal to ax plus b divided by x plus c has a horizontal asymptote at y equals 2 and a vertical asymptote at x equals -3, then what is a plus c? Well, if we have a horizontal asymptote as y equals to 2, that means that the limit as x is approaching positive and negative infinity of ax divided by x, that's equal to 2. Well, you're probably going to see these guys cancel. That means a has to be 2. So that's my horizontal asymptote. My vertical asymptote means my denominator has to be equal to 0. So I have, instead of x, I'm going to go ahead and write -3 plus c is equal to 0. Well, the only value that makes that work is +3. And so I just can go ahead and add those at a and that c together. So 2 plus 3 is equal to 5. For number 8, we're looking at the horizontal line, y equals 2, assuming x is bigger than 0. And y equals 2 is a horizontal asymptote. So here's my function. I have a horizontal asymptote. And so f of 0 has to be 2. Well, not necessarily. F of x can't be 2. Well, not necessarily. F of 2 is undefined. Well, not necessarily. D means this is our vertical asymptote, so hopefully you can see why A, B, and C don't work just from the graph that I just drew you. When we talk about a horizontal line, remember we're talking about E. That's the notation that we're talking about. When x is going to infinity, because x has to be greater than or equal to 0, so we're going to positive infinity. And if I have a horizontal line, y equals 2 is my asymptote. That's what it has to equal. It has to equal 2. And so the limit as x approaches infinity of f of x has to be 2.